Maybe I'll start now. All right, cool. Yeah, so I'm going to talk about detecting planets with microlensing. Microlensing is sort of, I think, the black sheep of exoplanet detection methods. If you go to an exoplanet conference, the microlensing people get stuck on the last day, and everybody is, skipping out and maybe confused and not talking about to them. Yeah, but I think that's hopefully on the cusp of changing in the near future, in particular because NASA will be launching Roman next year, which will be, among other things, conducting a survey of the galactic bulge, looking for microlensing planets, and will really open a new window into planets in a mass and orbital distance regime we haven't seen before. So just to give some context, I'll sketch in pretty crude terms a plot that if you've gone to exoplanet talks, you're probably sick of. But this is semi-major axis in AU. Versus planet mass. I'll do it in Earth mass. So there's, we'll call that 10, 100, 1, 0.1 down here maybe. So most of the exoplanets we know about are from Kepler, and they sort of sit in a cloud in this region. Of course, in our solar system, we have our Earth out here, sort of frustratingly right beyond the detection limits of what Kepler could achieve. There's also hot Jupiters.
Is that just because its reaction will fail?
It's also kind of hard to dig out an Earth-sized planet in terms of the photometric variability of stars that it observed. But with more transits, you would have been able to stack more of them and hopefully find a few Earth-sized things. So I think it's a combination of both. There's a hard cutoff here from where the reaction wheel failed. You couldn't stack enough transits, and then there's just, you can't beat the photometric noise going down this way. So it's sort of on the edge of both. RV surveys are good at finding things maybe out here in the sort of Jupiter mass regime. Of course, our, let me do 10 AU, Neptune and Uranus are sort of out here. I guess Jupiter is up here somewhere. And microlensing is particularly well adapted to finding planets sort of all over this swath right here. So, for the first time, we'll really be sensitive to planets like those in our own solar system in terms of their masses and separations from their host stars. Another thing that Roman will be finding is free-floating planets, so planets unbound from their star. And in fact, it's easier to think about microlensing from those, and we'll probably spend most of the time today talking about how you find just free-floating planets. And there's a nice connection between the planets you find out here and the free-floating planets that Roman will find, and that is the fact that if free-floating planets are ejected through dynamics in these systems, they really have to be sourced from interactions with planets that come out here. You can draw a sort of rough line of mass versus separation, where planets below this line collide with anything they scatter, and above this line eject. So it's not a very good line because we should be sitting below this line. This is why we have a moon. We ran into whatever we were scattering, whereas all our outer planets quite efficiently throw stuff out of the planet, out of our planetary system. They're responsible for forming our Oort cloud, for instance, possibly ejecting a planet 9. So it just turns out that when you're further out, you more efficiently eject things. And so you can draw a connection between Roman's detections of bound planets and free-floating planets. And so what is Roman doing to detect planets? It's using microlensing. So I figured I'd go over the basics of microlensing. And I'll confess this was sort of selfish because I'm not by any means an expert in microlensing. And I wanted to give this talk to make myself learn microlensing better. So hopefully we can all learn it together. So the basic picture in microlensing is that you're sitting here as the observer, and you're looking, say, towards the center of the galaxy. And fortuitously, there happens to be some lens here that passes along your line of sight to some background source. And so light from the source gets deflected by the gravitational effects of this lens by some angle. I'm going to draw things out of my own reach, unfortunately. Alpha. This is a general relativistic effect. And so you can ask, and so as a result, you'll observe some image up here. And so to go through how the locations of the lens and the source are related to where you form an image, I'll label some vectors here. So this will be an impact parameter vector. So I'm going to draw things with a vector on them. You can think of a sort of lens plane extending out of the board. And similarly, there's going to be a source plane. So this will be eta. And this deflection angle is going to depend on your impact parameter. And so we can relate where we, and so, oh, right. So we're going to call this a couple other labels, sorry. This is the distance to the lens, distance to the source. Right. And so this angle we're going to call theta. And we have some basic geometry that ds over dl times our impact parameter vector is equal to eta plus ds minus dl times this vector. And of course, I'm using small angle approximation throughout. And this is, of course, it goes without saying, not to scale at all. These are all very small angles, as we'll see in a second. And so what is this alpha? Sorry, alpha hat. This is going to be equal C squared over, let me make sure I get this right. C, right, okay. And so you can derive this within a factor of 2 by just using Newtonian dynamics and considering the impact approximation. So you can ask if you have something going by a body at a speed c, what's the deflection angle you expect? You would get half of this. And then you can take a whole course in GR to pick up the factor of 2. And this is the, I think, famous factor of 2 that won Eddington the Nobel Prize. Was it a Nobel Prize? No, not a Nobel Prize. No Nobel Prizes awarded, just fame in the papers. Okay, and it's debated, right, whether he actually measured it. at any rate, we're pretty confident it works
There was a
now.
1973 eclipse expedition that measured it.
Okay.
It's debated because most of it's caused by Jupiter, right? It's actually mostly caused by Jupiter.
This was the deflection. Yeah, 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 yeah. This was the deflection of some some star's angular position during. So this was from the sun, causing this deflection from light. Okay. Right. So yes, I'm gonna cop out on doing any GR today. You can ask maybe Reed or somebody else who's an expert in GR where that comes from. It would take us too far afield. Okay. So let's convert this now. We want an expression for theta. Oh, and another angle I'm going to label is the angle to the source. So how are these related? Right. Let me make sure. I want to define, so beta is going to be eta. Okay, I'm going to drop the vector hats now too, because we're going to think about just point masses. And so everything is azimuthally symmetric about the board. We'll go back to vectors later if we talk about what to do when there's both a star and a planet doing the lensing. But at any rate, so this will be, let's see, beta is eta over ds. And we have that theta, oh, right. We will define, okay, so we have C over DL is equal to beta plus ds minus dl ds. Oh, and this is going to just be theta, of course. Theta. So I'll write that up here for reference. Is hopefully that's clear from the picture. Ds, and then we have 4gm over c squared d l theta. Okay. And now we have everything in terms of angles. We're going to define a special angle called the Einstein angle, which will just be ds minus dl over ds times dl times 4gm over c squared 1/2. So that is this prefactor out here. Okay, and so the next step is to measure all our angles and units of this special Einstein angle. So we're going to call u will be beta over theta e, and y we're going to call theta over theta e. And so this gives us, let's see, we can take this, divide through by theta e, we get that y equals u plus theta, sorry, this is 1 over y. Or alternatively, u equals y minus 1. Okay, so we have a way of relating the angular location of our image measured in units of Einstein angle to the angular location of the source. And let me just give some numbers for typical Einstein angles. So this, there's another quantity that's usually a little more physical to work with. This is dl beta e. Sometimes you'll hear people refer to the Einstein radius. So that's a physical length associated with the Einstein angle. And this, for some numbers, is about 2 AU times m over 0.3 sum half L over, ds parsecs minus 1/2 rather. And then there's x times minus x over 0.25. And x is d s, sorry, d. Okay. In other words, so a typical mass of a star in our galaxy is about 1/3 of a solar mass. When people think about microlensing, we're thinking about looking at background sources in the galactic center, because you need a lot of, as we'll see later, this is a fairly rare event, so you need to look at a lot of potential sources to catch something microlensing. And this x is just the ratio of the lens to source distance. So if you have a lens that's halfway to the galactic center, you get an Einstein radius that's about 2 AU, which we haven't talked yet about detecting bound planets, but that gives you a sense of why microlensing is sensitive to things at the sort of few AU distance already. So if you have lensing by a star, and there happens to be a planet sitting right around the Einstein radius of that star, it's going to perturb the lensing signal that you get. And so it makes it especially sensitive to finding planets sort of at that distance separation. Okay, but I haven't said anything about how the actual lensing works, the magnification that you get that lets you tell that a lens is passed in front of a background source.
Sam, I have this, I remember reading the, Kaczynski first proposed the microlensing idea, and then he said the optical back to microlensing in galactic bulge is 10⁻⁶.
Yes.
Can we get that from here?
We can jump to that now if we want. Yeah, I was gonna go over how the magnification works and then talk about optical depth. But yes, so you basically, to foreshadow, right? This is the Einstein radius of a single source. We live in a galaxy. There's hopefully lots of lensing sources that can do lensing for us. And you can ask what fraction of the sky is covered by lensing sources within one Einstein radius, and it's about a part in a million.
So each star has a 2 AU little circle.
Yeah, so each star has a 2 AU little circle.
Distance between stars is
Distance between stars is, yeah, something like that.
that's how you
Right. Yeah, right. There's 10 to the 5 AU in a parsec, so that gets
Distance between stars
well
is
apart.
a lot smaller in projection. Right.
That's right.
That's why.
That's right. So I can say there's a slick argument, and I should mention a couple reviews that I'm shamelessly cribbing from. There's one by Shude and Mao. I think it's 08. This is a nice introduction, and there's a pretty thorough one by Scott Gowdy. From 2010. as well. So if you want a nice reference, those are good places to go. Okay, let me copy this and I'll do some erasing. That's why inverse. Okay. Right. Okay, so one can solve this for y. You just get a quadratic equation. So there's two solutions corresponding to the fact that you actually make two images in the image plane. So for a given source, you make two images. It turns out if you work through it, one is inside that Einstein ring and one is outside. And they fall at, let's see. Okay. And now you can ask what causes magnification. So you can say, if I have some area element, u du d phi in my source plane, what does it map to? What's the ratio between that area element and the element that it maps to in the image plane? So I'm using this y as a radial coordinate in my image plane, and phi is the azimuthal coordinate. So these are, there's no change in that. And so this is your magnification, like that. So let's work through what this is. This is 1/4u. I'll write it out, 1 plus or minus delta. I'm going to write delta for this. Times 1 plus or minus, let's see, that'll be u over delta. Okay. So 1/4u plus u plus or minus delta. Let's see, and then this is u squared over delta, right? Okay. So that is equal to 1/2 plus or minus 1/4u. This will be delta squared plus u squared over, write this out, and I'll go ahead and replace this with 2u squared plus 4. Okay. You can show, since u has to be positive, that one of these is positive, the one with the plus sign is positive, the one with the minus sign is going to be negative. So that corresponds to the magnification of your minus image, and that just means that it's flipped. And so it's inverted. If you look skeptical.
No, I didn't understand the sentence.
Oh, well, so there's two magnifications depending on which image you're looking at. Because there's the positive branch and the negative branch. If you, for any value of u, because this is is used greater than or equal to 0. The negative branch magnification is negative. So some absolute value that's larger than, it's larger than 1 in absolute value. But it's negative, and that's because the minus branch image is inverted. You still look skeptical. It's not critical to the story.
Spatial imagination.
Yeah, I'm not going to attempt to draw.
Yeah,
I think
one image is on the same side as the
right.
original source.
So okay, if you have
The other one is flipped and off.
right.
Also negative,
So if you make an image of this in the source plane, this is theta e here. You get one image. This is the plus branch. This is the minus branch. The minus branch, right? Your arrow would be flipped over like that. Yeah, yeah, right. That's why and so that's that's what I mean by a negative magnification. Right. Of course, well, I should have wrote down some numbers, but in practice, one never actually resolves these two images. It's on the micro-arcsecond scale or less. And so what you see instead for microlensing events is just the total light from both images. And so the magnification that one measures is going to be the magnification of the plus branch plus the magnification of the minus branch. And that is just 1 over 2, well, 2u times this piece, 4 over 4 plus u squared. Okay. Okay. So this is the magnification. So what does this look like in practice when you're observing something getting microlensed? Go ahead and erase this. All right. So now imagine one is looking into the board. Here's our lens, and there's some background source that's going to pass behind our lens like this. It'll reach some, and remember U is our lens source separation as measured in units of Einstein angles. So there's some minimum impact parameter U0. And so as a function of time, you'll just have U is equal to this minimum value plus T minus some time at which it reaches that minimum value, TE. Okay, where TE.
The magnitude of this current separation vector.
Yeah, I should probably, that's right. Yeah, that's right. Yes. Okay.
Yeah, a little square than you have to go as well.
Great. Thank you. Okay. What is this? This is R E over the relative tangential velocity of these two, of the lens and the source, or you'll often see it also written as the Einstein angle divided by the relative proper motion. It's dangerous to mix too many mu's into this talk, but you can afford one more. Okay, and so what you see, if you take this trajectory and plug it into the magnification, right? So this is minus TE. Let's say TZ, this is T0 minus TE. T0 plus TE. you get a curve that looks like that. And of course, the height here is just set by how close you come to the center of the lens. So if you happen to stray very close to the lens, you get a very big magnification like this. But it has a characteristic time scale of this Einstein time scale, which, so the really only physical information that one gets out of a microlensing light curve that's relevant for saying something about the lens is this time scale. So we can relate that to the properties of the lens. Let me, you get the magnification factor, but that's just how well, yeah, the chance encounter, how close you came to the center of the lens. So it's not really useful for constraining anything about your lens. So I'll put in some numbers. For what that is. Typical values, let's see. Okay, so TE is something like 20 days. We use our canonical 1/3 of a solar mass star. Again, DS over KPC F for a tangential velocity of about 200 kilometers per second. VT, and then there was that x1 minus x 0.25. Okay, so obviously there's lots of degeneracies for any one event, because in general, we won't know the tangential velocity of our source and lens unless we happen to be able to see the proper motion of the lens. Often, I guess, we'll know the distance to the source because we'll be able to identify and characterize the star that's getting lensed, and we won't know the mass of what is doing the lensing. So microlensing is sort of inherently a statistical exercise in that one measures a distribution of timescales from a survey. And since we have decent models for how we think the distribution of, say, tangential velocities are in the galaxy and where we expect to find things, right, in the context of, oh, I should mention, right, if you want to stick in an Earth mass here, this takes it down to the scale of hours. So it's totally, and for reference, Roman's planned cadence is to be taking measurements every 15 minutes, I believe, while it's doing its galactic bulge survey. So resolvable with Roman. We will not know the mass for, yeah, you'll never know the mass for individual events. You'll just have this time scale. There are instances, so when the angular size of your source star is bigger than the Einstein angle of your lens, you get what's called finite source effects. And in that case, modeling can give you direct constraints on the Einstein angle, but again, that's degenerate with the mass and the mass and the distance to the lens are degenerate in that case. So it's even in that case still statistical. Nonetheless, for any, oh, I should also say, you know, for any reasonable choice of these other parameters, if you see a microlensing event that's a few hours long, basically has to be something that's planetary mass. And there are a decent sample of sort of very short time scale events from ground-based microlensing surveys. There's OGLE, MOA, KMTNet, from which people have inferred that there's must be some sizable population of free-floating planetary mass objects out there. And if you run, or, you know, they do all the nitty-gritty modeling of coding statistical distributions for all these quantities. And when they do that, the number they quote is something like 20 free floating planets per star in the mass range of sort of Neptune mass and below. And the integrated mass is something like 80 Earth masses in that. Per 80 Earth, or 80 Earth masses per star in our galaxy. Well, yeah, stars are to 0th order and all in dwarfs, I guess.
What do you mean by the fact that it was statistical? As in like.
Right. Yeah. You know, if you just have a collection of Einstein timescales, right? That's what you're. I just mean that's all you have to work with, really, for thinking about free floating planets or stars.
You could combine Roman with ground-based. I think the current plan is that it'd be nice to combine Roman with CITA.
Yeah, there's another effect where if you have a different, and this I won't confess. I confess I don't really understand the details of it well. But if you have different baselines, or you know, two observations separated by a significant baseline, then you can get. Is it absolute constraints on the mass, or is it just the Einstein angle? I guess the distance to the lens, presumably, or something.
The efficiency or the mass per star again, because it might make more sense to express this in terms of mass per stellar mass.
Mass per stellar mass. Yeah, sure. One could.
So again, it was 80 masses.
This is the claim, yeah, 80. So I mean, this is based on fitting a power law to their handful of short time scale events. So it comes with
lens star.
Just per star in the galaxy. They're trying to. So this is just the. You mean what stellar mass? Down to what stellar mass?
I guess some point with mass function grades,
right? Yeah. Honestly, I'm just quoting the top line figure in the paper, and I didn't.
If it's per stellar mass.
Right.
It's going to be larger. So it could easily be that.
Right.
I mean, if this number is as this quote, it would be like 200.
Yeah.
Solar mass.
Yes. Yeah, I agree. Yeah. So I think so. One of the things I'm interested in talking to some other people about is just, does it even make sense with what we know about the mass available for planet formation, right? If you try to estimate from protoplanetary disks. Yeah. I'll also add the caveat that this number comes from the same group that was very wrong before about the number of free floating Jupiters. So they said there was 2 free floating Jupiters per star. And I think that's come down to, was it 0.1 now? Yeah, 0.1 or 0.2 maybe. They're both to me. Yeah. I don't know. Maybe that's not a good way to make judgments. I mean, there are. One would hope, right? Yes, that's the hope. I mean, my view is that you know, it's hard from the ground, and Roman will hopefully settle it. And so, yeah, it remains to be seen. But provision, I'll take it as a. I'll take the large number of short time scale events as meaning that in some sense there's a lot of free floating planets. I don't know if I'll put too much stock in 20 objects. I mean, it's sort of simple modeling too, right? They're just fitting a power law mass function for the free floating. So that's within, you know, you're sort of constrained by your model to end up with something, you know, based on that. So who knows if it's actually a power law.
Actually, I want to add actually a significant nature to show that the mass function is not parallel. So that actually got 2 distinct bumps.
This is for the bound population, right? Or this is, yeah. So, yeah. So I'm still talking about free floating planets. Yeah. Okay. Let's do optical depth. Microlensing optical depth. Another thing you'll hear people talk about, which is how common is it to find something like this? What fraction of the sky do you expect to be lensed at any given moment? And we'll get that number of approximately 1/1,000,000th, I guess. Okay. All right. So we're going to call tau the fraction of the sky that's covered by Einstein radii of sources. So the total area of the sky is 4 pi, angular area rather. And the optical depth is going to be the number of sources. So this is the number density. It's going to go from 0 to ds. Let's see, 4 pi squared. So number sources between T times angular area, it's just a solid angle covered by individual sources. All right. So let's be very simple-minded for now and just assume everything is the same mass. It'll turn out to drop out. We're going to write, if that's the case, all lenses mass m. And then in which case we can write n dl equals rho of dl over n. And we're going to write our integral now as rho that's rho over n dl squared. We have 4m gm over c squared s minus dl over ds dl. And as promised, masses cancel. Okay, let's be simple-minded again and just assume we have the constant density. Yeah, so we can pull out for g rho c squared. Let's walk with a pi up here. And I will just do the integral. You get squared, which we can rewrite as, sorry, that's not it. It's a 2. So we can rewrite this as 1 over 2 c squared times 4 pi over 3.
Why is it that scale like? There's a DDL on
I hope I did that right.
Sorry.
Yeah. I'll confess I'm basically just going by what I wrote here. G rho 0. I'm going to put this is ds cubed over ds. We're going to rewrite this 1 over 2c squared g m enclosed within the distance ds over ds. And we're going to write this as the circular velocity. All right. So the microlensing optical depth is roughly the circular velocity squared over the speed of light squared. And if you put in 220 kilometers per second, you get 3 times 10 to the minus 7. So
this is the circular velocity that from assuming that all the mass enclosed.
well, anything that has mass can lens, right?
The circular velocity in the actual galaxy comes from all the dark matter as well. So
Why can't dark matter lens? This was the whole point of inventing lensing.
just to be clear, if the dark matter is the lenses, then this gives you the optical depth.
Yes, I guess.
Another way of saying it is we could be thinking cosmological. Cosmological lenses.
Okay, I'll take your word for that. That sounds right. Yeah. Yeah. Yeah, I guess. Yeah. I mean, this is just a back of the envelope thing to get a rough sense of what the optical depth should be, and this is a number one should know for our galaxy, and this is a number you should also know. So it's a good way to just get the optical depth out. And so this is why it helps to look at a lot of stars to find things lensing. This is why Roman.
The dark matter is very, very thin, and the stars are
I guess that would give you a variable optical depth as a different, like your optical depth would be a function then of your sight line.
You kind of see the stars as symmetry.
Yes, yeah, I agree. This is very simple-minded. Right. Yes, presumably it's higher because you know things are scale height is that's right. That's right. So okay, take your geometric factors and put them in front of this. And I think that probably, maybe that gets you up to maybe more like 10 to the minus 6 or something. That's right, yeah. Okay, how am I doing on time? Oh, I have a lot of time. Okay, I don't know if it's gonna take a whole hour, but I'll talk about, I have time for binary lens, yes. I think so, yeah. I'm not gonna do anything too complicated. I'll just give you a flavor for how it works. Yeah, so that credit for that goes to this review by CITA Mao. But I thought it was pretty slick. Okay, so I said I put vector hats on this before because anticipating that we would be thinking about multiple things arranged in a given lensing plane. And if you remember, hopefully we had U and Y basically just being scaled versions of those. Basically they're angular projection on the sky divided by the Einstein angle. So we're going to promote U and Y to vectors. Our lens equation before was U equals Y minus 1 over Y. And now if we're thinking about multiple lenses arranged in the lens plane, this just gets promoted to Y minus Okay. To n y minus y. Okay. Squared. Okay. It's n. Okay. All right, so these little n's are just the mass of each individual lens divided by the total mass of the system. And this total mass of the system goes into the definition of the Einstein angle. So that's the scale that we're working with. Hopefully it doesn't strain credulity too much to believe that this is what you get if you go through a similar derivation, but now thinking about multiple lenses. Okay. All right. Let's see. So we're working with 2D vectors. Let's use complex numbers instead. So we'll have zeta be the source plane. So be u1 plus I u2. And then we'll use z for the image plane. So this will be y1 plus I y2, in which case we can write our lens equation as zeta is equal to z minus some k and k. And then this will be z minus zk over z minus zk bar minus zk bar. And I'll just go ahead and simplify that. Right. Okay. So in general, if you want to get the mapping from image plane to lens plane or vice versa for an in-lens configuration, it involves solving this, which turns out to be, I think it's a 2n plus 1 degree polynomial for the number of, based on the number, where n is the number of lenses you have. So for n equals 2, that's already a 5 degree polynomial. And so finding this mapping analytically gets pretty hairy. Well, I guess you can't solve it by radicals. And so I guess the rest of this will be necessarily sort of qualitative. And it gets really hairy doing multi-lens configurations. And it's a actually quite big open problem, I guess, in lensing, solving inverse problems from getting a magnification curve to going to lens configurations with 3 or more things. Even the binary lens case is somewhat difficult, but we can make a little more progress. For 2 lenses, right? So these, we can choose our masses. Mass 1 will be 1 minus q. Mass 2 we can set equal to q. And then we'll put z1 equals to minus q s. Z2 equals to 1 minus q s. So we're arranging our lenses on the real axis of the lens plane. Right, you have the freedom to do that, obviously. And so you can see that for a binary lens, there's 2 parameters that matter. For the lens configuration, there's the mass ratio Q, and then there's also the S is their separation, the separation of the two bodies, lenses in terms of Einstein radii. So there's two parameters that set the lens configuration, and then there's also the trajectory of the background source is another free parameter when doing sort of modeling of lensing events. And then the last thing I'll do is just sketch how one gets the magnification and determines a sort of forward model of what a lensing light curve looks like when you have, say, two lenses. So I'm going to leave this here. We'll leave that there too. Okay. All right, we're going to say lensing. We can think of as just some function that takes us what I was using from U1, U2 in the source plane, maps things to Y1, Y2 in the image plane. Okay. If you think, so the flux of some image say there's some region U, some subset of the source plane that's mapped into the image plane by this map. There'll be some specific intensity. And then we have du1, du2. So this is our solid angle element. We can rewrite this in our complex notation as dz. So this I/2 just comes from the Jacobian going from these real Cartesian coordinates to our complex ones. And now we want to know about what this corresponds to in the image plane. If you want to be a pedant, you can write it as the pullback of the intensity, but basically this is just the same intensity, but now evaluated in the image, in the source plane rather. So this will be a function of z bar. Sorry, zeta bar. I think I have two versions of this, and I think I copied the wrong one. Let me see. Okay, no, this is fine. Okay, and then this will be dz, d zeta, d z bar, d zeta bar minus. So this is the Jacobian of our coordinate transformation. The z bar, d z bar, d zeta. Okay. So this would just be our normal. So if there was no lensing, if this was just the identity, for instance, this would just be the same flux that one would measure. This would be right unity, and you would just measure the same flux. And so this factor here is a magnification. Okay, this is the determinant. Okay, it turns out it's a little easier to solve instead for the inverse magnification. So call this M. And so and the inverse is going to be D bar equals D bar D bar minus D bar D zeta bar dz. All right, we can read this off from this. All right, this is just one, as is this. And this will then just be one. And hopefully it's clear that this is just the complex conjugate of this. All right, so this is our inverse magnification. So we can take zeta, stick it in here. And so with if our inverse magnification is 0, then our magnification is infinite. And so we want to find where in our plane is this true? It's going to be when this is equal to 1. In other words, you could say that d zeta dz bar is going to be some complex number with unit modulus in some phase. Okay. And we can work out in the case of our binary lens here. This is going to be true when 1 minus q u bar minus c bar 1. No, that'll be 2 rather. Plus q c bar 1 equal to EVI phi pi minus c 1 squared. These are both squared. Okay. Okay, this is a polynomial in z bar. And so it's 4th degree, so there's 4 roots. And there's this parameter here, right? This could be anything. So if you pick one of the roots, right, you can think of it as a function of phi. And phi can go from 0 to 2 pi. So one of those roots will give you a curve in the complex plane, z bar. So that's in your image plane. And so this is almost what people call caustics. If you've ever heard somebody that come up in microlensing. Caustics is the same curve, but in the source plane. So you can map these curves to the source plane. And so these are the curves in the source plane where the magnification is infinite. As you can see, it becomes a bit of a numerical exercise to find these. Not all 4 roots will correspond to a curve. There's sort of a dizzying phenomenology of when you have different numbers of caustics and the sort of topological behavior when things are connected and stuff like that. That I won't get into, in part because I'm not an expert, but this at least gives you a flavor of how you can solve for where you get caustics in the source plane and how you can solve for the magnification of some image in the source plane as a function of its trajectory across the source plane, right? And yeah, you get a lot of phenomenology with things crossing caustics and stuff like that, that transfers to the light curve. And so as with anything in astronomy, the forward problem is somewhat easy enough, right? You could solve for the magnification if I would give you some lens configuration and the trajectory of the source. And then we're always solving inverse problems though, and that's much harder. And so that's how people find, but you model those light curves and you infer the configuration of your source or your lenses, and that's how you find planets. And you measure their mass ratio. I said there was two things, right? You can measure, so you can measure Q and you can measure S, ideally. And that's what microlensing measures.
Does your phone have to be away to not know that it's got a star next to it?
So the sensitivity starts to, it's a Q dependent statement, of course. And I think the number is maybe 5 or 10. Because microlensing is, I'm sort of working backward from numbers that I know, which is that microlensing is sort of ideally sensitive between 1 and 10 AU. And I said that the typical Einstein radius is about 2 AU. So that's a rough answer for a good number to have in mind. And there's, I think, lots of still unsolved challenges in doing the modeling efficiently. Even for binary lenses, but for higher end, certainly is difficult. And you can imagine that coming up in planetary systems if you had a pair of planets orbiting somewhat near the Einstein radius. All right. Well, I was reading I thought I had until the hour for some reason. Sorry for going long.
Is this how they also do